Hi, my name is Gwen. Welcome to chapter 4 of our quantum workshop series. And we are now going to talk about how we turn these circuits on. So, in the last chapter, we finished the blueprints. We have our laws, we have our minimal toolkit. And one of them is the C naught. So now it's not theory anymore. This chapter is where we prove that quantum computers are fundamentally faster than classical ones. So Deutsch-Jozsa, the first proof. We might mispronounce it, as I might, but this is the first time we mathematically proved the quantum computer could do something exponentially faster than a classical one. The problem is a simple binary. Is a function constant or balanced? Classically, to be sure, we might have to check half the database. With quantum, one query, one shot. Is the first proof that we aren't just calculating, we are interfering our way to the answer. So, the quantum trick of phase kickback, how does it actually work? When we run a quantum function, we don't just change the bit values, we leave the target in a special minus state. So when the oracle runs, it doesn't just flip the bit, it kicks back the answer as a phase change onto our input. So the answer is now hidden in the phase of our qubits, a property classical computers simply just don't have answers to. So we want to talk about all of these algorithms. One of them that's really well known is called Simon's algorithm, which is actually the bridge to Shor's. This is kind of like the exponential precursor to Shor's. It solves a periodic problem by finding a hidden string S. The quantum computer gives us clues in the form of linear equations, and then we hand these clues to a classical computer to solve. So this is our first hybrid algorithm, quantum for the very heavy lifting and classical for the final crunch. So we mastered phase kickback and the interference trick. And it's kind of very similar of how you're trying to daisy chain what is really currently known and what can exist. So we've only just scratched the surface of what phase information can do. In chapter 5, we'll take that phase control to the next level using the quantum Fourier transform to solve the hardest problem in cryptography. And again, if you have issues or if you find that this content is too far ahead, just kind of use these main phrases, right? And try to do a little bit of exploratory diversive digging on your own. I find that sometimes just knowing where to start is kind of part of your own journey and the own process of how everybody else learns, right? Thank you.